Hey guys, in this video we're going to look at the hypothetical question of what if we did example 19 with two concentric spheres, but the inside object is, instead of being a conductor, an insulator. Okay, all right. I can only make that so exciting, but okay, if it's a Gauss's law problem with concentric objects and the inside object is an insulator, it's barely different from the scenario where the inside object is a conductor. Or at least it's barely different if you're talking about concentric spheres, which we are in this case. All right, so now let's sort of dive into it, right? In the case where it was a conductor, the field everywhere inside of it was 0. Now that it's an insulator, that will no longer be true. All the rest of my answers from example 19, which were covered in the previous video, don't change. Right? The field outside of it at 5 centimeters or 10.5 or 15, those answers are all fine. Nothing actually changes about my analysis because the rule is if you're outside of a sphere, the field that it creates is basically kq over r squared. You can prove that using Gauss's law, and we have done that. We did that back in example 16 in your notes packet. All right, now, what if it's an insulator, but we're not outside of it, we're actually inside of it? That's where there's going to be a difference. All right, now, what I'm going to say about that is we did this in example 16. In fact, if you go look back at your work and you find example 16, all this here, this is example 16, all over again. Okay, fine. So let me explain what's happening kind of in each line, just because I don't want to rewrite it. And then we'll say what the answer is, and then fix the graph from part F. And then we are done with the question of what if they are concentric spheres. All right, this is just Gauss's law. Next line. If it's a solid insulator, that's when you tend to use rho. And so my enclosed charge then is going to be rho times the volume enclosed. Oh, how much volume is enclosed? I didn't really mark that on here. It's asking about the electric field at 2 centimeters. This is a 3 centimeter object, so there we are, something like that. So that means that the volume of charge enclosed is that much, whatever that is. Right now, whatever that is uses little r. The volume of a sphere is 4/3 pi r cubed, but the r that I'm using here is the little r because I'm not enclosing the whole sphere, right? I'm not enclosing all of this. I'm only enclosing that much, right? Just a portion of it. Therefore, we use the little r. The one quirky thing with spheres, if you recall, is that rho can't stay in the answer. It's got to become q over v. And the reason for that is that up here in the prompt, they told you the charge of the sphere was q, not anything with rho, right? It says q. Therefore, rho has to disappear from my work, and I've got to replace it with the total charge over the total volume. If you can read that, it's a big R down there. Okay, bunch of stuff cancels out. You should be able to churn through the algebra, especially if you look back at example 16, but you get q little r cubed over epsilon naught big R cubed. Great. Final step. Our electric field then is q r, because 2 factors of little r cancel, over 4 pi epsilon naught big R cubed, or, if you recall, 1 over 4 pi epsilon naught is actually k, so you could write this as k q r over big R cubed. All right, now this was not a symbolic problem. You'd be plugging in numbers here, but suffice it to say you could do that on your own if you really cared about what the number would be. But little r would be 0.02, big R would be 0.03, because that's what they said the radius of the inner object is. Great, that's it. We could get an answer for it. Now, on to part F, because everything else in between is exactly the same, because we're outside of the sphere, and then we're just more and more outside of it. Nothing changes. Let's fix it. There. All good. That's literally all that was required to make the correct graph for part F. The reason for that is that this corresponds to the electric field function of kq little r over big R cubed. It looks like a scary function, but in fact the k, the q, and the big R are all constants. Therefore, this is effectively like you're making a graph of y equals 2x. I mean, it's not quite like that. It's like you're making a graph of e equals, I don't know, 5,000 times r. But you can understand that as being like y equals 2x. It's a line.